All right, guys, let's talk about non-parametric tests. We're going to be going over chi-square mainly this week. So let's zoom out and look at the big picture. So what exactly is a parametric test and what is a non-parametric test? So let's break it down from the beginning and go through it. So parametric tests are kind of like those friends who only show up if everything is just right. They've got really high expectations. So a parametric test is going to be used when we want to test something very specific, like a hypothesis about certain population parameters. And that might be the mean or the variance. So you're dealing with numeric scores. So you think of things like results, weight, height, hours of sleep, all of those things have to do with math. The problem is they have strings attached. They make certain assumptions about the data. They assume that the data is normally distributed. They assume that the data is measured on an interval or ratio scale, and they assume homogeneity of variance. It means the variances are equal across the groups. So examples of those would be t-tests, ANOVA, Pearson correlation. On the other hand, non-parametric are a little more chill. They're a little more flexible. They don't need perfection, and they just kind of work with what they've got. So instead of numeric data, you've got things like categories or classification, like labels, like yes or no, or male or female, introvert versus extrovert. And they're going to focus on frequencies and broader patterns. And one of the best things about non-parametric tests is they come with fewer assumptions. So you can use them if your data is a little off, like if your data set is skewed, or if you've got a small sample size, or if you're dealing with categorical variables. So 3 examples of non-parametric tests are chi-square, Mann-Whitney-U, and the Kruskal-Wallis test. We're going to be dealing with chi-square only. So how do we know when we should use a parametric versus a non-parametric test? Well, first of all, as long as certain assumptions are met, and we're going to talk about what those assumptions are, parametric tests are going to be preferred because they're very much more precise. They are specifically designed to analyze numeric and normally distributed data, and they are good for working with interval and ratio scales. However, if you can't meet certain assumptions about your data, non-parametric tests are going to be better. What situations would that include? First of all, it's going to include situations where your data violates assumptions, such as being skewed, not normally distributed, unequal variances, which would mean we don't have homogeneity of variance. If you've got extreme variability in your scores and extreme outliers, your measurements are categorical instead of interval and ratio, and you've got missing, undefined, or extreme scores. Those would be situations where you would be justified in using a non-parametric test. So you may find yourself in a situation where your data violates one of those assumptions, and you may find yourself in a situation where you need to turn your data from numeric scores into categories. And that's okay, because if you can change your data from a numeric score and group it into a category, that opens up the possibility of doing a non-parametric test. So there are also other situations where this would be useful. It might be more simple to collect and interpret categories. That's a justification. Your scores might be too inconsistent to be reliable, another justification. Or instead of using raw values, you want to use original rankings. Those would also justify the use of a non-parametric test. So we're going to start looking at an example here about how this would fit into doing a chi-square test. So if you look at the data on this slide, you're testing the question, is soda preference associated with gender? So we want to know if the preference for Coke or Pepsi is different between men and women. And the data underneath there are organized into what we call a contingency table. And that's the perfect setup for a chi-square. So what we have here is a table with our options of Coke and Pepsi, okay? And then we have our male and female. And you can see here 19 males preferred Coke, 10 females preferred Coke. 6 males preferred Pepsi, and 15 females preferred Pepsi. And if you sum this across male and you sum across female, you'll see you have 25 and 25, which would be a total of 50. As with any statistical test, there are some assumptions and restrictions we have to keep in mind. In order to have trustworthy results, the first thing with a non-parametric test is we have to have what's called independence of observations. And independence of observations simply states that each frequency, each observation is generated by a different individual. In other words, you only have one quote vote. So one person equals, one person equals one data point. So you can think of it as one person, one vote. Another assumption or restriction is the size of the expected frequencies. So in a contingency table for a chi-square, we need the expected frequency in each cell to be at least 5. So you're going to calculate what's called an expected count in a cell in your contingency table, and that cell should have a minimum value of 5 as the expected score. Anything above that's fine, but anything below 5 is not acceptable, and you would not use a chi-square. So why is this important? It's because if your expected numbers are too small, the way the chi-square formula is set up, it becomes unstable. And if you continued with the test, the results you would get would be unreliable. So in other words, if a cell is too empty, your test is going to get cranky. All right, let's talk about the chi-square goodness of fit test and walk through what it is used for and how it is basically calculated from a mathematical standpoint and the formula. So again, a chi-square test is going to be designed to examine whether the observed proportions in your sample match the proportions you would expect based on a theory or knowledge about that population. So we use it to test one categorical variable with multiple levels. So for example, a categorical value might be soda, the type of the, preference for soda. Multiple levels would be Coke, Pepsi, Mountain Dew, Dr. Pepper, Barq's root beer, whatever. So you're basically asking the question, does the pattern in your data fit what we would expect to see? So in a chi-square goodness of fit test, we have a null and an alternative hypothesis, just like any other statistical test. Our null hypothesis is going to say something like the observed frequencies match the expected frequencies. Okay, there's no difference between the observed frequencies and the expected frequencies. We could either say there's no preference among categories. So in other words, people like Coke, Pepsi, or Sprite equally, or the population matches a specific known distribution. So perhaps the soft drink company is stating that they've done some huge analysis out there, and they say that in the general population, 70% prefer Coke, 30% prefer Pepsi. You could do your own sample, and you could run your own chi-square goodness of fit, and you could compare your outcome to their population parameters. Our alternative hypothesis would just state that there was a difference. So our observed frequencies do not match the expected frequencies. It could be verbalized as either there's a preference among categories or the population differs from the known distribution. So what we're doing is we're going to be counting observed and expected frequencies. Our observed frequencies, F sub O is the actual counts of people or items from your sample. And remember that each participant is only going to be placed in one category. So you can only like Coke or Pepsi for this particular scenario. You cannot have more than one data point that's related to you. Observed means this is what you saw happen in your data. Our expected frequencies are the counts that we'd expect in each category if the null was true. There's a formula that we use for that, and that is the calculated with this formula right here. F sub E for expected equals P times N. P is the proportion predicted by the null hypothesis. So for example, if you're saying out of 100 participants, if there was no difference in preference, I would expect 50 participants to like Pepsi and 50 to like Coke, okay? And that is multiplied times the total sample size. So basically you're calculating what would happen if there was no effect or if there was no difference. So again, here you can have two types of null hypotheses. You can have the no preference or equal proportions. So example, it says if each category is expected to have equal frequency, you have 100 people choosing between 4 sodas, you would expect to see 25 in each group. And then known population comparison, say I have 70%, 30% based on Coke's, Coke's going out there saying we've done this and this is what we found. So now you have the data to be able to use those proportions to compute your expected counts and then determine if your hypothesis should be retained or rejected. So what does the chi-square test do? It's going to compare those observed frequencies to expected frequencies. Helps us decide whether the pattern is due to a difference or if it's up to chance. Okay. Our chi-squared formula right here, chi-square equals the sum of the square of the frequency of observations minus the frequency of expected observations. We're going to square that over frequency of expected observations. So FO is observed frequency, F sub E is expected frequency, and the formula adds up the squared differences between what we saw and what we expected, divides it by this, and that gives us our chi-square. So how do we interpret the statistic? Well, the bigger the result, the bigger the statistic, the more your data differs from your null hypothesis. So you're going to compare the chi-square value to the chi-square distribution to see if it's statistically significant. Your cutoff, if you looked at that chi-square distribution, depends on the degrees of freedom. Degrees of freedom equals C minus 1, where C is the number of categories. So again, if your test statistic falls in this critical region right here, then we would reject our null, and we would say that our alternative hypothesis is what we need to adopt. So this is an example of part of that chi-square distribution table. Of course, you're not going to be having to consult this table because SPSS is going, I'm sorry, I apologize. Jamovi is going to help you along with your decision by simply providing you with p-values that you need to interpret. Remember, when you're interpreting a p-value, you're looking for a p-value that is less than the established parameter for rejecting the null, which for this class is p is less than 0.05. So let's walk through an example scenario. We're going to talk about which mascot is preferred by UHCL students. A sample of 50 students was asked to choose their favorite mascot. You had hawk, egret, ibis, or blocky. And I hope ibis is the correct pronunciation. I don't know if it's ibis or ibis, but we're going to go with ibis. So in my data here, I have an observed 18 for the hawk, 17 for egret, 7 for the ibis, and 8 for blocky. So my null hypothesis is that there's no preference. Each mascot is equally likely to be chosen at 25%. So you'd have 25 hawk, 25 egret, 25 ibis, 25 blocky. And then your alternative hypothesis would be that there is a preference, at least one mascot is more or less popular than expected. So I have my observed frequencies here and I have my expected frequencies here. So I observed 18, I would have expected to see 12.5, 12.5, 12.5, 12.5, and you can see what I did observe right up here. So I'm going to use the formula F sub E equals P times N to get 0.25 times 50 equals 12.5. That was how they calculated what we should see. All right, this scary looking math here is simply them working out what we just talked about. They're taking F sub O minus F sub E, so 18 minus 12.5. They're squaring that and divided it by 12.5. And they're doing that for all four observations. So you've observed 18, observed 17, observed 7, observed 8, etc. They calculated this out to get the interior, 5.5 squared divided by 12.5, etc. Now you're down to 30.25 over 12.5, etc. Then you get down to 2.42 plus all of this. That's where you're summing, and they get a statistic of 8.08. And they're going to calculate their degrees of freedom by categories minus 1. There are 4 categories of mascots. So 4 minus 1 is 3. So the degrees of freedom is 3. And if they go back and look at that chart, your critical value for alpha equals 0.05 and degrees of freedom of 3 is 7.81. Our calculated statistic, 8.08, is greater than 7.81. So this is stating that there is not an equal preference between the mascots. In other words, there is a mascot that is preferred, at least one mascot that is preferred more than others. So chi-square can also be used as a test of independence. So let's talk through that. All right, so we can use a chi-square test to evaluate whether two categorical values are related. So in other words, we're looking at checking if knowing something about one variable, like whether or not they're in a certain treatment group, gives you information about another variable, like their outcome or their performance outcome based on their treatment group. So think about it as asking the question, does membership in one group affect the pattern of responses in another group? So a test of independence is set up to help us evaluate a relationship between two variables, such as here I have the variables of being in a certain group, and the group is drugs or no drugs, and the outcome of a chess match. You can win, lose, or draw. So participants are either going to be, they are going to be classified into two variables at once. So each person is going to fit in one cell of this 2D table. So they're either going to be in the experimental versus control, and then they're also at the same time either going to be in win, loss, or draw. So these 12 people right here are wins in the experimental group, and they're not going to appear in any other group. And that allows us to be able to do this chi-square test of independence. So our null hypothesis is going to give us a statement that says that there is no relationship between the two variables. Okay. So if that happens, the proportions across all your categories are going to be the same for both groups. Okay. So your performance on this task is the chess match is going to be independent of whether or not you took the experimental drug or not. And then your alternative hypothesis would just state that there is a relationship somewhere between group and performance. So performance in one of those, the wins, losses, and draws are going to be different depending on whether you were in the drug group or the control. So remember, we have our observed versus expected frequencies. Our observed frequencies are based on the data that we have collected. They simply show how many participants fell into a certain category combination. So again, the first example that I talked about there were 12 participants in the drug group that were also in the winning column of their chess match. Expected frequencies are calculated based on what we would expect to see if there is no relationship. Okay, so you have F sub E, which is expected, is equal to FC times FR divided by N, where FC is the total for the column, and that would be total wins if we were looking at that one column there. Times FR, which would be the row, okay, and N is my overall sample size. So again, expected frequencies are what I would expect to see if there was no relationship between these two variables. So why does all of this calculation stuff matters? We use those values to calculate our chi-square statistic, and the larger differences we get between observed and expected, suggests that a relationship exists. It makes sense thinking about it, right? If there is a relationship between certain variables, and say the drug does help you make better decisions in a chess match, then you would expect to see more wins in the group that was receiving the experimental drug. To me, a chi-square test makes so much sense. It's just very simple, and the simplicity of it is kind of beautiful. Because I have these two groups, I know how many people are in those groups, and based on that, I can say how many I would expect to see if there wasn't a relationship. So chi-square test statistic and the degrees of freedom, it's going to be the same formula as the goodness of fit test. So we have chi-squares equal to the sum of f sub o minus f sub e squared over f sub e. The chi-square distribution is the same. We're not going to be using the distribution because you're going to be using Jamovi. But you would calculate your degrees of freedom as r minus 1 times c minus 1, where r is your rows and c is your columns. So in this particular analysis right here, for rows, I have 2, and for columns, I have 2. So r minus 1 is 1 times c minus 1 is 2 minus 1 is 1. So 1 times 1 is 1. So your degrees of freedom in this situation would be 1. All right, so here is another example, and this is going to be part of your assignment for this week. This is kind of the basis of it here, but go look at this example of a physical, the plan to get a physical health exam, right? Do plans to get a physical health exam differ by sex? So you have a sample of 150 students, and there are 60 males and 90 females. And they were asked a simple question: do you plan to get a health physical? And they could either respond no, maybe, or yes. Okay. All right, so let's look at our null and our alternative hypotheses. So our null hypothesis is going to say in the general population, there's no relationship between sex and plans to get a physical. So in other words, our males and females are going to respond using similar proportions. And then our alternative hypothesis is saying that in the general population, there is a consistent relation between sex and plans to get a physical, or in other words, the distribution of answers is going to be different by sex. And this is our contingency table. I have males and females. I have no, maybe, and yes. And remember, I had 60 males and I had 90 females. So this is going to be useful for calculating your degrees of freedom. I have 2 minus 1 times 3 minus 2. I'm sorry, 3 minus 1. So 2 minus 1 gives you 1. And 3 minus 1 gives you 2. And 1 times 2 is 2 for our degrees of freedom. And that's going to be useful later. So here is the calculation of the expected frequencies. So you take your no males, your maybe males, your yes males, and then the same thing for females, and you calculate all of these things right here. So those are our expected frequencies for each row and column intersection. And you plug all of that in, or you let Jamovi do that for you, and it's going to calculate a chi-square statistic of 8.22. And remember, on the other slide with the contingency table, I helped you arrive to a degrees of freedom of 2. So if you go back and looked at a table of your critical values for the chi-square statistic at an alpha level of 0.05 and degrees of freedom of 2, our critical statistic is 5.99. Our calculated 8.2 right here is greater than 5.99, which indicates we have a significant relationship between sex and plans to get a physical. So do males and females differ on whether or not they plan to get a physical? Absolutely, they do. So based on that, we need to go and kind of do a post hoc type test to look at effect size. And we have 3 different options for being able to do that. depending on what kind of data we are collecting and the levels of the variables that we're collecting. We can calculate a Cohen's W when we use proportions instead of frequencies, okay? And there's your statistic, the formula right there. Again, it's in Jamovi. We can also calculate a phi coefficient, where this phi right here, the Greek letter phi, is the phi coefficient is calculated when you have each variable with two values. And then we have one more. The third one is a Kramer's V. Kramer's V is calculated when at least one variable has more than two values. All right, so let's go over how you would calculate all of these lovely chi-square tests in Jamovi. So let's look at an expanded version of that same particular question we were looking at a minute ago. We're going to assume a team of researchers is studying health behaviors in college students, and they want to know if gender is related to plans to get a physical in the next 6 months. They looked at 150 undergraduates. They asked them their gender, male or female, and their plans to get a physical in the next 6 months. So we are looking at conducting a test of independence, a chi-square test of independence, and we're looking at the relationship, if there is a relationship between gender and getting a physical exam. So our basic research question is there a relationship between a student's gender and their plans to get a physical exam? Why are we using chi-square? Because both of our variables are categorical. Our null hypothesis would be that there's no relationship between gender and decision to do a physical exam, and our alternative would be that there is a relationship between gender and the decision to get a physical exam. So what you're going to do is you're going to go into Jamovi and you are going to go to analysis, you're going to go to frequencies, and you are going to select independent samples. And that is right over here, independent samples, and you see chi-square test of association. You're going to move gender to rows and plans to columns. Under your cells, you're going to make sure that you have selected both observed and expected counts. Why? Because that's what your assignment is going to ask you to provide as well. So you're going to make sure under your options for this test that you've selected the chi-square. Okay. We're going to go with our hypothesis is just group 1 does not equal group 2. And under cell counts, make sure you've hit observed and expected. So when you have ran your test, you're going to get observed and expected values. So this just gives me an example of what I should see and what I did see. Or you could take this and calculate all this out by hand if you so really wanted to. But, you know, I think Jamovi is wonderful in that it does this for you. But you at least know what formulas this was based on, right? So for females, observed for maybe I should have seen 41 and I saw 39. For no, I should have seen 16.8 and I saw 15. And for yes, I should have seen 25.8 and I saw 30. For males, I should have seen 32.6, I saw 35. For expected, I should have seen 13.2 and I saw 15. And for yes, I should have seen 20.2 and I saw 16. So I've got my observed, my expected underneath here, all of my sums there. If I let Jamovi run the chi-square, the value of chi-square is 2.35 with 2 degrees of freedom, and it's marking a p-value of 0.39. So 0.309 is greater than 0.05. So since it's greater than, I am going to retain the null. There is no difference between these groups in this particular association with these two variables. So again here, chi-square value was 2.35 with 2 degrees of freedom. P-value is 0.309. The p-value is greater than 0.05, we are going to retain or fail to reject, same language, I like to say retain the null, because remember, we're pessimists in statistics and we always assume that there's no relationship. So instead of failing to reject the null, I want to say I'm going to retain it. So what does that mean? There is no statistically significant relationship between gender and plans to get a physical in that particular sample. So your assignment, I'm going to also include a short video going over that. Your assignment here is on the next slide. So you're going to have a chi-square assignment and an associated data set. Download the data set, download the assignment, and follow the directions to answer the questions, and then submit it. Pretty simple.